18 months ago, an OpenAI model won gold at the hardest math competition on Earth. Then another model cracked a problem nobody had touched since 1946. Now they're saying the newest one just solved 10 problems that the entire field of mathematics had basically given up on. 10 problems. 8 different fields of mathematics. Some had been open for years. Some for decades, and one of them had been sitting there for 27 years. And this time, there's something different about the claim. You don't have to simply trust OpenAI. You can check the proofs yourself. So a simple question arises: if Astra can solve these questions, which none of us can solve, then how close is Astra to AGI? Or is it already there? Before jumping to the AGI topic, let's first understand what the claim itself is. So, on August 1st, OpenAI published a post called 10 Advances in Mathematics and Theoretical Computer Science. And under this, they claim that the work came from an internal version of a model they're calling Astra, their next major model, not yet released to the public. The claim is simple, and it's exactly what it sounds like. 10 open problems, 10 answers. These results are spanned across 8 completely different areas of mathematics, like group theory, operator algebras, high-dimensional geometry, quantum complexity, lattice cryptography, extremal combinatorics, coding theory, and circuit complexity. One of the biggest results was the construction of the first ever non-Sophic group. Back in 1999, mathematician Mikhail Gromov introduced the idea of sophicity. A Sophic group is one whose structure can be approximated, arbitrarily closely, by large finite permutation systems, basically by shuffling cards. Every group mathematicians had examined had turned out to be Sophic. Nobody could prove that every group had to be, but nobody could construct an exception either. That question stayed open for 27 years, and Astra apparently built the exception. Another result disproved the Kahn's rigidity conjecture posed by Field's medalist Elaine Kahns in 1980. The other results included the first improvement to high-dimensional sphere packing since 1978, along with 3 problems from Paul Erdős's catalog of unsolved questions. Thomas Bloom, the mathematician who runs the official Erdős problems database, called the August results big news mathematically larger than anything he had seen from AI before. So the claim is extraordinary. But here's the important question. How do we know it's true? Normally, if an AI says it solved 10 problems nobody else could solve, you'd have to read the papers. And that's a problem. You'd need specialists in 8 different areas of mathematics. They'd have to independently inspect the arguments, find hidden assumptions, check every step, and decide whether the reasoning actually works. That can take months or years. And humans make judgments. Different mathematicians can disagree about whether an argument is complete. And OpenAI here did something different. They published the proofs in Lean 4 on GitHub under an open license. So let's first understand what Lean actually is. Lean is a formal proof checker. You write the mathematics as code, and Lean's internal kernel checks every logical step. If the next step follows from everything that came before it, the proof compiles. If a single step doesn't follow, it fails. No reading between the lines. No, this part is probably fine. No benefit of the doubt. It's mechanical verification, and there's an especially useful feature in Lean. If you want to skip a step you haven't actually proved, you can type the word sorry into the code as a placeholder. So when the proofs were released, one of the first things people checked was simple. How many sorries are there? The answer across all 10 proofs was 0. Every step, very proof, nothing skipped. That matters because the verification isn't coming from OpenAI's marketing team. It's coming from a compiler. And because the files are public, anyone can download them, build them, and see whether Lean accepts them. That's an unusually strong verification mechanism for an AI capability claim. But it has one very important limitation. Lean can only check whether the answer follows from the question. It cannot check whether the question was written correctly. Taking a famous open problem written in human mathematical language and translating it into formal Lean code is still a manual job. Humans have to decide exactly what the original conjecture means, and that's difficult. If the formalization accidentally makes the original problem weaker, Lean can produce a completely flawless proof of something mathematicians never actually asked. The code passes. The mathematics is internally consistent, but the AI may have solved the wrong problem. So the real question becomes, do those 10 Lean formalizations actually match the original mathematical problems? And honestly, after this explanation, you got the answer that compiler can't answer that. Working mathematicians have to, and that's where the independent evidence becomes important. And to check those I spend a week tingling around the web and find something interesting. In May, an internal OpenAI model disproved the Erdős unit distance conjecture, which had been open since 1946. Tim Gowers, a Fields medalist, reviewed the result and publicly said he would have recommended it for a top journal. 9 other heavyweight mathematicians, including Noga Alan, wrote a companion paper explaining the AI's reasoning to the broader mathematical community. They didn't just say the result looked interesting, they built on it. That matters because these are exactly the kinds of people who would be capable of finding a serious flaw. And then there's Thomas Bloom. His reaction carries even more weight, because if you don't know about him, Bloom has already caught OpenAI making a mistake in this exact category of claim. Back in October 2025, Kevin Weil, then a vice president at OpenAI, posted that GPT-5 had solved 10 previously unsolved Erdős problems. Bloom checked. GPT-5 hadn't discovered new solutions. It had searched the mathematical literature and found existing solutions that Bloom personally hadn't yet cataloged on his website. And OpenAI presented those as new discoveries. Bloom called it a dramatic misrepresentation. Google DeepMind CEO Demis Hassabis called it embarrassing, Well deleted the post, and he later left OpenAI. So when Bloom looked at the August announcement and called it big news, that isn't just another positive reaction. It's coming from someone who has already demonstrated that he's willing to call OpenAI out when the mathematics doesn't support the claim. The October claim was essentially, trust our announcement. And this time, the August claim is, here are the formal proofs. Run them yourself. And Bloom is saying this time, the results are real. That puts the two announcements in completely different categories. Now let's know how much electricity it costs to solve these problems. So as in the post, they also published the cost $2,000. OpenAI said the compute cost for all 10 proofs was roughly $2,000 at current API rates. That number is real, but it's not the number you might think it is. Noam Brown, one of OpenAI's researchers involved in the test time reasoning methods Astra relies on, pointed out what the figure leaves out. The $2,000 counts the successful runs. It doesn't include all the failed searches that went nowhere and never made it into the repository, and surprisingly, OpenAI didn't disclose what those attempts cost. So the actual cost of discovering the 10 proofs is still unknown and definitely more than the stated amount. That doesn't make the results fake. It means the efficiency story is incomplete. And the same thing applies to the papers themselves. Human researchers polished the final write-ups before publication. The model produced the mathematics, while people formatted and prepared the final papers. How important that human contribution is depends on what you think the difficult part of mathematical research actually is. And that question becomes much more interesting when another AI gets involved. Now, after all this shit happening in just less than 24 hours after the announcement, a mathematician at Anthropic named Levent Alpoge posted something that made the Astra story considerably more complicated. He said, after 24 hours, I have half of them solved with Fable. So Fable is Anthropic's publicly available model, not a secret internal system, a model which you can use today. Alpoge used a generic prompt, switched off internet access, and reproduced 5 of the 10 proofs, half, within a day. And this cuts in 2 completely opposite directions. On one hand, it's extremely strong outside corroboration. If the lean formalizations were fraudulent, or if the problems had been quietly weakened to make them easier, a competing model working from a cold prompt without internet access shouldn't simply reproduce the same answers. Fable getting 5 of 10 is evidence that the underlying mathematics is real. But there's another interpretation. If a publicly available model can reproduce half of these historic results within a day, then Astra may not represent some completely unique level of intelligence. Astra solved 10. Fable solved 5. The gap is real. But the ceiling may be much lower than OpenAI's announcement makes it sound, and that leads to a much bigger possibility. Maybe we're not watching one company suddenly reach a completely new level. Maybe multiple AI systems are reaching roughly the same threshold, at the same time a threshold where sufficiently capable models can actually contribute to mathematical research when they're given a well-defined target. If that's what's happening, the story is bigger than Astra. But there's one major piece of evidence pointing in the opposite direction. Earlier this year, Terence Tao and a group of mathematicians ran a very different kind of test. They took 10 genuine, live research problems from their own ongoing work. They weren't selected because an AI might have a shot at them. They were actual problems mathematicians were working on. The problems were sealed. AI models available at the time were given a fixed window to solve them. Every single problem remained out of reach for a single AI prompt. Humans had to solve them. Now put those results next to Astra. Astra closes a 27-year gap in group theory. AI fails every problem sitting on Tao's desk. Both things can be true. And the reason is probably the most important distinction in this entire story. Astra is extremely powerful at searching a solution space once the space has been defined. Tao's problems require something different. You have to decide which direction is worth pursuing. You have to recognize an unexpected connection. You have to decide which dead ends aren't worth another week of work. You have to formulate new ideas when there isn't an existing map telling you where to search. That's a different capability, and it's exactly where the AGI question becomes complicated. There's another test that makes the same point from a different angle. Riemann-Bench contains 25 brand new research-level mathematics problems written from scratch. Each problem took its author weeks to construct. The problems weren't selected because an AI might be able to solve them. They were designed to resist the approaches existing models were good at. When the benchmark launched, frontier models performed terribly. The best score was around 6%. Nobody even reached 10. But by the middle of this year, top scores had climbed into the 60s and 70s. That's the number worth paying attention to. Not because 60 or 70% means AI is now a mathematician. It doesn't. The important thing is the speed of the climb. Problems specifically designed to resist AI went from almost completely inaccessible to being solved at surprisingly high rates in a matter of months. The frontier is moving fast. Now, after looking all this thing, we need to separate two abilities that often get mixed together. The first ability is, give an AI a difficult, well-defined problem and let it search an enormous solution space until it finds a valid answer. Astra provides extremely strong evidence that AI is getting very good at this. The second ability is very different. Give an AI an open-ended environment and let it decide what problems matter. Formulate those problems, choose a direction, pursue it, recover from failure, and produce discoveries that humans didn't know to ask for. That's closer to what we intuitively mean when we talk about general intelligence. And the evidence there is much weaker. Astra can apparently take extremely difficult mathematical targets and push through them. But the evidence doesn't yet show that Astra independently decided those targets were important. Humans selected the problems. Humans formalized them. Humans prepared the final write-ups. And when researchers gave AI completely open-ended problems from ongoing research, the results were much less impressive. That's the distinction. Solving a hard problem is not the same thing as deciding what problem is worth solving. Now the part you all were waiting for, so the Astra is AGI? Maybe this is the wrong question, because the evidence from this announcement doesn't cleanly say Astra is AGI, but it also doesn't look like ordinary AI anymore. The proof's compiled with 0 gaps. The code is public. Independent mathematicians are checking the formalizations. The person who previously caught OpenAI misrepresenting a math discovery called these results big news. A competing lab reproduced half of them with a public model in a day. And research-level math benchmarks have improved dramatically in a very short period of time. At the same time, we still don't know whether every formalization perfectly captures the original mathematical problem. We don't know the true total compute cost. And we don't know whether the capability extends to the kind of open-ended research problems that humans choose and formulate themselves. So I wouldn't call this proof of AGI. I'd call it something more concrete. That AI is moving from solving problems to participating in research. And that's a much bigger shift than another benchmark going up by a few points. Because the next frontier isn't simply, can AI solve a hard problem? We've already seen that so many times, according to me. The next question is, can AI decide which hard problem is worth solving? Can it look at the world, identify something nobody else has noticed, formulate the question itself, decide how to attack it, survive weeks of failure, and eventually produce something genuinely new? If it can do that reliably, the AGI conversation changes completely. And maybe that's the real milestone we're watching. Not the moment AI solved 10 impossible problems, but the moment we stop having to tell it which problems to solve.